Hello everyone. So guys, I hope you people might have tried the DPP of steam turbines and you might have got a good feeling about the steam turbines. So in case anybody of you have got any doubt, then we can solve these questions and then we can see how different topics are actually covered or how the concept of steam turbines are covered. Okay. So it says, which of the following statement is correct for a steam turbine? This question is a multiple selection question. Okay. So you can have more than one statement to be correct. So it says it converts pressure and energy into electrical energy. So a steam turbine is not actually converting pressure energy into electrical energy. So steam turbine converts, or steam turbine actually develops mechanical work. Okay. So this is not a correct statement. It says it converts thermal energy into mechanical energy. Yes. So you have steam at high pressure, high temperature. That is the thermal energy which is contained in the steam. Okay. So your steam turbine actually converts the thermal energy into mechanical energy. This is a correct statement. Again, it says it converts thermal energy into kinetic energy. No, that is a wrong statement, because the energy that is received, or the energy that is developed by the turbine, is actually the mechanical work. Okay, so the third statement is again wrong. Next says it converts low grade energy into high grade energy. Yes. So it takes in the energy from the fuel. So the fuel, when it burns, it produces heat. So that is the low grade energy that is converted into the thermal energy. That is again low grade energy. And that thermal energy is actually converted into work. So work is your high grade energy. So this statement is also correct. Okay. So if you see now, the two statements are correct. So the option will be B and D. Is it clear to everyone? Okay. Moving on to the next question. It says the main aim of compounding of steam turbine is to. So why we actually compound the steam turbine? So you see that when we were discussing the steam turbine, we had seen that if there was no compounding, whole of the energy was converted into the kinetic energy. So delta H, it was converted into V squared divided by 2 delta. Okay, and now you see that since H was significantly high, this was very high. You see that was leading to very high velocities, and due to very high velocities, the RPM of the machine that you were getting, it was coming out to be beyond the power generation values. Okay, so the RPM was very high, so we do the compounding basically to reduce the rotor speed. Is it clear? Okay, so now if you say that it says improve efficiency, that is not correct. Sorry. Next it is reduce steam consumption. Again, this is correct. It says reduce motor speed. That is correct. The last one is it is reducing the turbine size. That is also not correct. Okay. So these three statements are wrong. This one is the correct statement. So to reduce the motor speed, or you can say to reduce the turbine speed. Is it clear? Next it says which of the following is not the correct statement for steam turbine. He is asking not the correct statement. So it says an impulse turbine. In impulse turbine, the cross section between the blades is constant. So we have seen that in case of impulse turbine, the passage area, that is the cross section, it remains constant, and that is the reason why your VR1, VR remains constant. Okay, and when it remains constant, that means there is no reaction component that is coming. That means this is a pure impulse turbine. So this is a correct statement. So we know that this is a correct statement. Blade manufacturing of reaction turbine is complex. So yes, that is correct statement. Generally, the reaction turbine blades are profile blades. So you have to cut specific profile on the blades. Okay. So this is how the profile has to be cut. The symmetric blades are like, they are symmetric. Okay. You have a symmetric type of profile over here. But these blades are adjusted according to the profile. At a lower point, at a higher point, everywhere the profile changes. So because of which the manufacturing of these blades becomes little costly. So this is again a correct statement. In reaction turbine, the pressure drop takes place only in the moving blade. So in case of a reaction turbine, you see that the reaction turbines are mostly impulse reaction. They are not purely 100%. So had this statement is, if in 100% reaction turbine, the pressure drop take place entirely in moving blade. So that is a correct statement. But he has not written 100% reaction turbine. Reaction turbines are basically reaction impulse turbine. So you see that this statement is wrong. Next is impulse turbine as used for small power generation. That is again a correct statement. We don't use impulse turbines for mostly power generation. So these are limited to very small installations. Okay. So now you see that these are the three correct statements. This is the wrong statement, but he is asking which is not the correct statement. So once he is asking which is not the correct statement, the answer would be your option C. Is it clear to everyone? Okay. So I hope everybody might have understood this. Moving on to the next question, it says steam expands from the enthalpy of 3400 kilojoule to 3200 kilojoule in a nozzle. The velocity of the steam coming out of the nozzle will be. So you see that this is a nozzle, okay, and from this nozzle the steam is entering over here and it is getting out over here. So this is your location 1, this is your location 2. So this is your location 2. So if your steam is entering from location 1 to 2, you see that we know that in case of a nozzle, generally the nozzles are adiabatic devices and there is no work extracted. So whatever is the enthalpy drop that takes place, H1 minus H2, that is directly converted into the kinetic energy V2 square minus V1 square by 2. Okay. So now you see that he has written that the steam expands from enthalpy in a nozzle. Generally, V1 is very, very small. V1 is in the range of 0. When steam is entering the nozzle, that is entering at very low velocity. So we almost reduce it or we almost neglect it. So this becomes V2 square divided by 2. So now you see that you have written H1 minus H2, that is equal to V2 square divided by 2. H1 is given as 3400. So 3400 minus 3200 multiplied by 1000. This is your kilojoule per kg. So if it is kilojoule, so this is your joule. That will be equal to V2 square divided by 2. Is it clear? So this will be your 200 multiplied by 1000. There is another 2 that is equal to V2 square. Okay. So now you see that this is 400 multiplied by 1000. So 400, this is how your V2 square will come. Is it clear? So now you see that the velocity V2 will be equal to, this is 20, this is 20. So 20, this will be 1, this will be 1, square root of 40. Square root of 40 will be equal to 6.36 or 6.32. Okay. So it will be 632 meter per second. Understood? Yes or no? Is it clear? So the velocity will be coming out as 632 meter per second. So the option number B will be correct. Okay, this was again a very easy question. Moving on to the next question. This question is of combined cycle. So it says a combined cycle power plant works with Brayton cycle as top cycle and Rankine cycle as the bottom cycle. If efficiency of both the cycles is 40%, then the efficiency of the combined cycle will be. So you see that how this cycle actually works. If you want to understand how does the combined cycle actually work, I hope you people might have studied combined cycle, or you might have studied only the formula of combined cycle in thermodynamics. If not in basic thermodynamics, we can see over here. So if you want to see the temperature entropy diagram, so you see that this is how your Rankine cycle will be moving. So your Rankine cycle will be moving something like this. Okay, and you see that energy is added over here, QS. Whatever is the energy that is getting added over here, that is coming from the Brayton cycle. So you see that your Brayton cycle would be somewhat moving something like this. Okay, both are different cycles. Understand, these two are very different cycles. Okay, this is your 1, 2, 3, 4. This is your Brayton cycle. It will be moving something like this. So what happens in combined cycle is whatever is the energy that you are rejecting to the atmosphere. So whatever is this energy that you are supposed to reduce, or whatever is this energy that you are supposed to dump to the atmosphere, that energy would be actually supplied to your steam power plant. Okay, so you can simply write it like this, that there is a Q1 that is coming over here. This is your W1 and this is your Q1 minus W1. Okay, now this is going into another cycle and this is your W2 and this is your QR. Okay, so this is how your cycles are moving. Understanding? So this is your cycle 1, this is your cycle 2. Okay, so in case of this process, if your efficiency of cycle 1 is efficiency 1 and efficiency of cycle 2 is efficiency 2, then the combined efficiency of combined cycle, that is equal to W1 plus W2 divided by Q1. That will be equal to efficiency 1 plus efficiency 2 minus efficiency 1 efficiency 2. Okay, so this is, you can derive the result, this one. So this will come out to be 0.4 plus 0.4 minus 0.4 multiplied by 0.4. So that will be equal to 0.8 minus 0.16. That will come out to be 0.64. Okay, so the combined efficiency of the cycle is 64%. You see that this efficiency is much higher than the individual efficiency. So you see that your Brayton cycle, which is developing 40% efficiency, maximum efficiency 40%. Again, this is maximum 40%. When you combine both of these, the total efficiency has increased to 64%. This is what is actually happening nowadays. Most of the power plants that are installed nowadays are combined cycle because the efficiency is significantly higher. Understanding? Okay. So the answer to this question will be, the efficiency will be 64%. Is it clear? Okay, understood everyone? Okay, now let's go to the next question. Next question was again a very easy question. It says, in a simple impulse turbine, the nozzle angle at entrance is 30 degree. What will be the blade speed ratio for maximum diagram efficiency? So we see that for maximum diagram efficiency, maximum, for this condition we have calculated that the rho is equal to cos alpha divided by 2. Okay, that is what we have calculated. So this will be equal to, rho is equal to cos alpha, that means cos of 30 divided by 2. Cos of 30 is 0.8 square root of 3 divided by 4. Okay, 1.732 divided by 4. Okay, so that value will come out to be, I think, 0.43. Is it clear to everyone? I hope this is correct. Understood? Okay, if it is understood, now let's go to the next question. It says, at a stage of 50% reaction turbine, the rotor diameter is 1.4 meter and the speed ratio is 0.7. So your rho is 0.7. Okay, if the blade outer angle is 20 degree, then the maximum efficiency of the turbine is, I think this question is slightly out of syllabus. You can consider this. What I will do is, I will remove this question because this is again going into very deep. It is this much is not required actually. Okay, so we will leave this question. I will remove this question. Moving on to the next question, it says, a de Laval turbine has absolute velocity at entry and exit to the blade as, a de Laval turbine has absolute velocity at entry and exit to the blade as 250 meter per second and 150 meter per second. So you have V1 is equal to 250 meter per second and V2 is equal to 150 meter per second. Is it clear? The work developed by turbine per kg of the steam flow will be. So you see that this is de Laval turbine. De Laval turbine is an impulse turbine. If de Laval turbine is an impulse turbine, the work done or the power developed will be simply equal to V1 square minus V2 square divided by 2. Is it clear? So impulse turbine, the energy or the power that is actually the power that is extracted is purely the change in kinetic energy. Okay, so you can calculate. So he has given you m dot. So kilojoule per kg he is asking. So power developed per kg will be equal to V1 square minus V2 square by 2. So that is equal to 250 square minus 150 square divided by 2. Okay, so 250 square is 25 is 625, 0 minus 15 is 225, 0 divided by 2. So that will be equal to 40, 0 divided by 2. That is 20 kilojoule per kg. Okay, so the power that is developed by the de Laval turbine will be equal to 20 kilojoule, or work developed will be 20 kilojoule per kg. Is it clear to everyone? Everybody understood this? Okay. So if you have understood this, now let's go to, we have come very fast to the end of the questions. Okay. So it says a 4-row velocity compounded steam turbine develops 6400 kilowatt. What is the power developed by the last row? Okay. So you see that this is a Curtis turbine. So we have velocity compounded. Okay, we have velocity compounding of the blades. So when you have velocity compoundings, we have already seen that in case of velocity compounding, you might have seen while we were drawing the velocity diagram with the stages, we have seen that in the nozzle, your velocity increases significantly, and after it is going, it increases by certain amount, then it remains constant, then it decreases, then remains constant, again it decreases, then it remains constant, decreases, it remains constant. So you see that velocity compounding takes place like this. So this is your velocity, this is your stages. Okay, so you see that this is where your nozzle will be. So this is your nozzle, this is your moving first blade, this will be your stationary first blade. Okay, so this is your moving blade and this is your stationary blade. Again, this will be your moving blade and this will be your stationary blade. Okay, so you see that in case of generally the compounding of Curtis turbine, we drop the velocities almost like equally in all the stages. This is what is the Curtis turbine is actually designed like. Okay, so you see that if your velocity is 600 at the inlet, so and there are 6 stages, so velocity will be dropped 600 by 6, that is 100 meters per second. So velocity will be 600 at the entry of the first stage, 600 over here, then the next it will be 500. Once it is entering 500, 400, 400, 300, 300, 200, 200, 100, 100 to 0. So that is how generally your velocity is moving. So 600, 500, 400, 300, 200, 100 and then 0. Okay, so this is how the velocities are there at the entry of each row. So at entry of first row, it will be this, second, third, fourth, fifth, sixth, and it will be exiting at 0. So now if you want to see how much is the energy that is converted into work. So energy that is converted into work is 600 is the entry and 500 will be the exit. So in the first stage, you see that your entry will be at 600 and exit will be at 500. What is the energy that is converted? Energy converted will be 600 square minus 500 square divided by 2. Okay. What will be the energy converted in second stage? So over here, it will be entering at 500 and it will be exiting at 400. So the energy that is converted into work is 500 square minus 400 square divided by 2. Okay. So similarly, you can do this calculation. So 400 square minus 300 square divided by 2. Then you have 300 square minus 200 square divided by 2. So once you do these calculations, you will come to know that the power that is developed among these stages, okay, the power that is developed among these stages is 6 to the square is 36 minus 5, 25. 36 minus 25 is 11, 11 by 2. So it will be 11 by 2 multiplied by 100 square. This will be 25 minus 16, that is 9 divided by 2. So 9 divided by 2 multiplied by 100 square. It will be 7 divided by 2 multiplied by 100 square. It will be 3 divided by 2 multiplied by 100 square. And the last will be 1 by 2 multiplied by 100 square. So you see that the energy that is converted, or energy that is converted into work in the first stage, is 11 by 2, 9 by 2, 7 by 2, 3 by 2, 1 by 2. So what is the ratio of energy that is converted? So you see that the ratio converted is 11, 9, 7, 9 minus 2 is 5. Okay, 5, 3, and then 1. Okay, so the ratio of power converted is, it is moving something like this: 11 ratio, 9 ratio, 7 ratio, 5 ratio, 3 ratio, 1. So you see that this is going from 1, 3, 5, 7, 9, 11, 13, 15, 17 like this. So he says you have a 4-stage velocity compounded. So in case of a 4-stage, what we will take, we have only 4 stages. So if you have only 4 stages, so last stage will be 1, second is 3, next is 5, next is 7. So the total power that will be distributed in the ratio of 7 is to 5 is to 3 is to 1. This is how the power will be distributed. Okay, and if this is how the power is distributed, now you see that the ratio total power when it is distributed, it is coming out to be 7 plus 5, 12, 12 is 13, 15 plus 1, 16. So you have 16. So power in the last stage, will be, so you see that out of 16 joule, only 1 joule is extracted in last stage. So it will be 1 divided by 16 multiplied by the total power that is extracted is 400. So this will come out to be 400 kilowatt. How about the second last? Second last will be 3 by 16 multiplied by 6400. Okay, so this will be 1200. What will be next? Next will be 5 by 16 multiplied by 400. So then you have 5 by 16 multiplied by 6400. So that will be equal to 2000 kilowatt. So you see that the power that is developed is 4, 12, 20 and then 35. So 35 plus 20, 55, 7 divided by 60, so 28. So 28 plus 20, 48, 48 plus 12 is 60, 60 plus 4, 64. So the total power developed will be equal to 6400 kilowatt. Okay, so the power developed in the last stage will be 400 kilowatt. Is it clear to everyone? Yes or no? Yes or no? Clear? Okay, so if it is clear, then let's go to the last question of this DPP. So last question was again a very easy question. It says a Parsons turbine has absolute and relative velocity at entry to the blade as 250 meter per second and 150 meter per second with the nozzle angle as 30 degrees. The work developed by the turbine will be. So he is saying that if we draw the velocity triangle of a Parsons reaction turbine, so this is how the velocity triangle is looking. Okay, so this velocity is 250 meter per second. This is your 150 meter per second, and you see this angle is your 30 degree. Is it clear? So this is how your velocity triangle is looking. So I can complete this velocity triangle. Wait a second. This is little bit deformed. Okay, so I will draw it properly. So let's take help of lines, straight lines. Okay, so this is your straight line. Then you have here will be your absolute velocity coming. Okay, and here is, let's say, your relative velocity coming. Okay, similarly you have your absolute velocity coming over here, and then you have, relative and absolute coming over here. Understood? And then this is your VF. Okay. So this is how your velocity triangle will be looking. So this angle is your 30 degree. If this angle is 30 degree, you see that this angle will also be your 30 degree. Is it clear? This is your velocity 250 meter per second, and this is your velocity 150 meter per second. Is it clear? Okay. And you see that this is your velocity V2. This is your this is your velocity V1, and this is your VR1. This will be your velocity VR2, and this will be your velocity V2. So now he is saying what is the power developed. So for calculation of power developed, he has said, he has not given you anything else. So that is okay. Okay. So we need to calculate other angles as well. Okay. So this is given as 250. So if this is given as 250, we can calculate what is the component of this in this direction. Okay. So 250 cos 30. Cos 30 is square root of 3 by 2. Okay. So we can calculate what is the whirl component VW1. So VW1 is 250 multiplied by cos of 30. Okay. So this is 216.50. So VW1 is equal to 250 cos of 30. That is equal to 216.50. Okay. So this total will be 216.50. Is it clear? Also you can calculate VF1. So this is your VF1. This will be equal to 125 meter per second, because 250 sine of 30. 250 cos 30, 250 sin 30. So this is your 125. Okay. So now you see that this is your 125, this is your 150. Can you calculate this? Okay. So we can calculate what will be this component. So this component will be equal to square root of 150 square minus 125 square. So square root of 150 square, okay, minus square root of, wait a second, 150 square minus 125 square. Okay. So that is 6875. So square root of 6875 is 82.91. So this becomes 82.91. If this is your 82.91, you will see that this will also be equal to 82.91. Why? Because we have this to be replicating like this. Okay. So the same triangle will be replicated over here. This will be your 125. V2 will be your 150, and this will be your 250. It is Parsons reaction turbine. So now we need to calculate what is the work done. So work done will be equal to VW1 plus VW2 multiplied by U. Okay. So we will calculate U. U will be equal to VW1 minus VW2. That is equal to 216.50 minus 82.91. 50 minus 82.91. Okay. So 216.50. So this comes out to be 133.58. So 133.58 is your U, meter per second. Understood? Is it clear to everyone? Okay. So now you have calculated U and you have calculated VW1, VW2. You can calculate power. So power per kg of the steam flow will be equal to, VW2 plus VW1 multiplied by U. Is it clear? Okay. So this will be equal to VW1 is 216.50 plus 82.91 multiplied by 133.58. Is it clear? So I can write 216 0.50 plus 82.91. So this comes out to be 40 kilowatt. P by m dot s is coming out to be 40 kilojoule per kg. I hope everybody is getting this answer only. Yes or no? Is it clear? Is it clear? Understood? Okay. So guys, if it is clear, then we have come to end of our DPP of steam turbine. So guys, the question which or the syllabus which is there in GATE, probably in that very simple question will be asked from the steam turbine, though there have not been many questions which have been asked in GATE. Earlier time, the questions that were asked in GATE were quite lengthy as well, like in 2005, 2006. So at that time, there were few questions asked from the steam turbines. But in recent like 15 years or so, we have not come across any question that is very difficult. So question will be very, very easy. Okay. So I hope everybody might have been able to solve the question. Okay. Thank you. Thank you so much.